listen up here, and now we're going to go to the theory part about this lecture, about this lab. Earth's magnetic field. Okay, first of all, what is the Earth's magnetic field? Well, if you look at it like, here's the Earth, which is kind of, this is a globe. I got the whole world in my hands. I got the whole. Okay, Earth's magnetic field. It's like as if it's a dipole magnet, a bar magnet, and it's 11 degrees off center at a tilt from the rotational axis of the Earth. Okay? So what happens as a result of that is the magnetic North Pole is not the same place as the true North Pole, the rotational North Pole. Now I said in the last video that it's in Greenland. That's what I remembered from when I was in high school, but as it turns out, Earth's magnetic field moves about 40 kilometers a year or so. And I guess it's moved to Canada now. So I must have gone to high school back in the 1780s or something. No, I just must have remembered it wrong. Okay, so what causes the Earth's magnetic field? Well, if we look at a model of the Earth's core, why don't you come over here so you can see this in here. I hope you can see this. But what you have is in the center you have an inner core. Does anybody know what the inner core is made up of?
Liquid.
No, the inner core is solid nickel. Iron. Nickel and iron. And around that we have a outer core which is liquid iron. Alright? And around that we have the lower mantle, then the upper mantle, and then Mickey mantle. No, just kidding. And then we have the crust. Alright? Now Earth's magnetic field is caused by the rotation, the movement of the liquid iron relative to the lower mantle. That frictional force there, creates the Earth's magnetic field. Now there's three things that you need actually to create the magnetic field. And that's a conducting fluid. We've got that, called the liquid iron. It's conducting iron, and it's a fluid, liquid. And there must be enough energy to cause the fluid to move with sufficient speed and with the appropriate flow pattern. Why does this core move, the liquid core? What makes it move? What do you think? The Earth is rotating, that's why. It's really that easy, okay? It's not hard. And then there must be a seed magnetic field. This one's a little bit squirrely where this comes from. But there has to be a magnetic field to start. And there was. And we think it came from the sun, but we don't really know. This isn't a geophysics class, so we'll just leave it at that. But it's very important that we have all those. Now the math behind all this and how it creates the Earth's magnetic field is very complicated and is beyond the scope of this class. It involves vector calculus and it's really pretty boring, so we'll skip it. Okay, so what else do we need to know about it, the Earth's magnetic field? Like I said, it's not entirely stable. It moves, the North Pole moves around. It's been moving around a lot. Not only does it move around the location, the magnetic field intensity changes. In fact, in the last 150 years, it's gone down by about 10%. What does that mean? Does that mean in 1500 years it's going to be gone forever? That would be bad.
Yeah.
We'd have to leave.
It's okay, we'll be dead.
You got someplace to go?
I'll be dead, it's alright.
Oh, it's okay, you'll be dead. Alright. No, actually, it'll be okay because there's significant variation in the Earth's magnetic field. And it's been that way historically. This is well within the range. It goes up and down, 10% is no big deal. More importantly, every once in a while, the whole thing flips! And north becomes south and south becomes north. Cats and dogs living together. It's awful. And that's where blockbuster movies come from. In 2012, and it's all because of the Mayans.
It's a great movie, quality film.
Yeah, it doesn't make any sense, but it's okay. It's a good movie. Those flips happen, anywhere between every 100,000 years to 50 million years in between. It's somewhat random, and we don't really know what causes it. There's some theory that it might be doing for asteroid collisions, for example. Might happen at the same time. Can't tell for sure. The last one was 780,000 years ago. Long time. So somewhere in the middle. So, maybe it will happen now. Or maybe it won't happen for another 100,000 years. I'm not going to worry about it. Okay. So that's what happens with the Earth's magnetic field. Now, even across the Earth, the magnetic field varies a lot too. The strength of it. In fact, it varies from 25,000 to 65,000 nanotesla. Wow. That's pretty cool. Alright? But the lowest points are actually, you would expect, because you're furthest away from that bar magnet, the lowest points to be around the equator, but it's not. Actually, the lowest intensities are down in South America somewhere, and in parts of Africa. Okay? But more importantly, about the intensity, is what's called the declination. Now that's the angle between true north and magnetic north. Now you would think that that angle is always going to be, related to the fact that your compass is always going to point directly to a magnetic north. But it doesn't. Okay? There are certain parts of the world where it's off from magnetic north by plus or minus, off of true north by plus or minus 20 degrees. Why is this important? Now, what is it off here? Does anybody know what it's off? What the declination is here? You're supposed to look it up before class.
Is it 61?
No, that would be the inclination. I'll give it declination.
14?
14 degrees. Okay? So, that's kind of significant. And what that means is, if you wanted to use this as a compass, the compass has some limited value because you have to know how far off you are in terms of your declination. And to know that, you have to have a map essentially of the world showing what the declination is versus where you are, and you have to know where you are. In which case, who needs the compass? Not to mention that nowadays we have GPS. Now, incidentally, to figure out where true north is, the first people to do this were the ancient Egyptians, at least the first that I know of. And the way they did it was kind of interesting. What they did is they built a circular wall. The Egyptians were a lot better at building circular walls than I am. There's the center. And what they would do is they would wait at night, and they would get the position of a star as it crossed over the wall. Let's say right there. Let's say it's called Betelgeuse. And then they would wait until Betelgeuse set. And what they did is they drew an angle like this and like that. And if you bisect the angle, that would be true north. Now, how do we know this? Well, this is how the Egyptians built the pyramids. Okay? If you look at the Great Pyramids of Giza, for example, they've got one side of each is facing one of the cardinal points of the compass, north, south, east, and west. Okay? So that is how you find true north. But there's a problem. Essentially what it comes down to then is that using the stars is a very effective means of navigating. But we didn't use the stars aligning it, we used compasses. Why? What was the advantage the compass had over steering by the stars?
During the day?
Exactly. You see, stars are not really all that useful at daytime. They're only useful at night. And so what you could do is you could use the stars to figure out where you were at night, and then use something called dead reckoning in the compass to figure out where you are during the day. Now, dead reckoning, incidentally, was never alive. Actually, dead reckoning comes from the word deduced reckoning, and it means I know where I was, I know which direction I'm going, and I can figure it out from there. Okay. But the problems with declination and all the variations in it across the world, that did lead to a lot of distorted maps. So if you look at a lot of maps from like the 1200s, 1300s, you see like all the shapes are kind of distorted, and a lot of that had to do with problems with declination. Okay. What else does the Earth's magnetic field do for us?
Shield us from rays.
Rays. Who's Ray? And why do we have to be shielded from him?
Them.
Them.
Yes.
There's more than one?
Rays. Yeah.
Rays. What kind of
Cosmic rays.
Yeah, well, it shields us from the solar wind. If it wasn't for the magnetic field, the solar wind would strip away the ozone layer, leaving us with no protection, which would strip away the atmosphere, and then we'd all die. This is what happened to Mars, and that's why nobody lives on Mars now, except for John Carter.
Wait, that's the premise of that movie?
What?
That's the premise of that movie?
No.
Okay.
I'm just bringing it up because the movie just came out.
Alright.
Incidentally, the intensity, like I said, is currently decreasing, but it's not something to worry about. I said that already. Okay. So does anybody have any questions? Oh, I forgot! This is a video! That's right. I'll see you in the physics lab.